So what I want to talk about now is what's called Euler's method. We've learned another method which students tend to find confused with this called Newton's method, which is a way of using tangent lines and their x-intercepts to estimate the zeros of a function. And it was an iterative process where you kept repeating it until you got to your desired level of accuracy, as long as your first guess didn't have a derivative of 0, which would cause a horizontal tangent line that doesn't have an x-intercept. But the idea would be you guess an x-intercept, find the tangent line for that x, find its x-intercept, then go through, find the tangent line for that x-intercept, calculate the new x-intercept, and so on. That was Newton's method. Euler's method is not used to find x-intercepts for functions. It's used to find y values, or I should be more accurate, it's used to estimate y values. And it also does it by using the tangent lines. But instead of x-intercepts, we're going to be looking at y values. And for this, if we're going to be using Euler's method, I'm going to kind of go through graphically. We have a slope field where we only use the slope field at certain points, but that doesn't mean that we couldn't draw slopes in at other points. And the idea being that we're going to build a sketch of a curve using small pieces of tangent lines, which if smoothed out would give us an estimate of our particular solution. And this is a way where everybody can sketch the same particular solution and get to the same estimated y value. It's the repeatability that math and science really likes. So here we have a slope field for our differential equation. I guess I should actually write that, where we're looking at dy dx equals x plus y. And this is a slope field for 9 points. And we are given an initial condition where we are going through 2, 0. So we have this point as our initial condition. And we can see from there that we do have a slope of 2. So we know at 2, dy dx is equal to 2. Well, if we're going to do Euler's method, we have to have a step that we're going through, what's called a step. What that means is how much are we counting the x's by as we go to a desired x value. So let's say we wanted to go and figure out what f of 3 is going to be about, again, as an estimate. So let's say we want to count by 0.2. So if I'm at 2 now, that means I'm going over to 2.2. And to find the y value there, well, I know at 2, 0, I have a slope of 2. So if I were to go up until I get to an x of 2.2, this should be about what my y coordinate would be for my function. So to find that y value, I need the tangent line at 2, 0. Well, I know the point 2, 0. I know the slope 2. So my tangent would be y equals 2 times x minus 2. Well, at 2.2, in other words, plug 2.2 in for x, y would be 0.4. And if you notice from my sketch, that's a pretty good estimate. So I then say, well, what if I go 2.2 further on, or 0.2 further on to 2.4? Well, I need to know the tangent line at 2.2. So at 2.2, the slope is going to be 2.6, which would look about like this. A little bit steeper than 2, but not as steep as a 3, slope of 3. And I get my tangent line, which if I plug in what the y value 2.4 is, I get about 0.92. So my sketch isn't the greatest, but it's that idea that everybody who's doing this method is getting that y is about 0.92 when x is 2.4. So then I carry on. What if I go on to 2.6? Well, I need the tangent line at 2.4, which has a slope of 3.32, giving me a new tangent line. I plug in the 2.6 for x on this tangent line. You get y is about 1.584. And I want to keep doing this. Oops, sorry. I want to keep doing this until I get to my desired x coordinate, which then yielded a y estimate of 3.46496. And this is consistent. Anybody who correctly uses this method will get that exact same estimate.